sort of logistics that we can go ahead and discuss while we wait for Jinji to sign back in. So I'm Gretchen Keppel-Alex. I'm at the University of Michigan, and I'm one of the external co-chairs of the Biogeochemistry Working Group. And I'm joined by Abby, who can introduce herself.
Hi, I'm Abby Swan. I'm the other external co-chair of the Biogeochemistry Working Group. I'm at the University of Washington. And our NCAR counterpart, Matt Long, is the new NCAR co-chair and is unable to join us today, but we do have a recorded presentation from him, and he gave the update to the large group on Monday, if you want to go back and watch that if you didn't catch it.
Yeah, so the way we're structuring the session today is we're starting off with a keynote from Jinji Liu, who is leading carbon cycle modeling efforts at JPL focused on assimilating observations of the Earth system, generally space-based observations of the Earth system, to develop a process level understanding of carbon cycling and biogeochemical cycling. And so we thought that would be a nice kickoff to the first section of this, where we will be presenting a few strategy talks to try to generate ideas and community feedback about where we can go next with the Biogeochemistry Working Group. So we'll have a series of 5-minute talks designed to be sort of thought-provoking about future directions for BGC after Jinji's talk. And then we'll have about 20 minutes for breakout groups, so we can sort of gauge interest and hopefully refine some of those ideas based on community interest. Following that, we'll have a break, and then 4 talks that look at ocean biogeochemistry, another short break, and then 4 talks that are more focused on land biogeochemistry. And during those breaks, we'll have breakout rooms open so that if you want to use that time for sort of informal networking, you'll have the option to do so. So I don't know, Abby, if you have anything else you want to add.
No, I think that's great. We have hopefully not too many technical difficulties, but we'll see how it goes. I'm really excited to have Jinji joining us today to hear about what you're working on in the NASA sphere.
Thank you so much for the invitation. So I will try to share my screen to see whether it works now. Can you see my screen now? No.
No, not yet.
Okay.
Do you want to try, did you email your presentation to someone other than Elizabeth? Because we could do Matt's talk first and then come back and do Jinji's.
Yes, please go ahead. Yeah, you can come back to me. So I could email to
email to me and Gretchen, and hopefully one of us can share it.
Okay, thank you. Sorry about this.
Okay, so we're gonna start then with Matt Long's talk. Does that make sense, Gretchen? Or wait.
Yeah, I think so.
Yeah, he was first on the agenda. Okay, so I will share Matt's talk. Oh wait, hold on. I have to do it again. There we go. All right.
Hello, I am Matt Long. I'm a scientist at NCAR, and I'm a new co-chair of the Biogeochemistry Working Group. I am sorry I can't be with you in person today, or virtually in person, but I'd like to share a few words about some ideas I have for strategic directions for the Biogeochemistry Working Group. I've chosen to encapsulate my ideas in the context of this pyramid here, which entail, the bottom levels of this pyramid entail things that I think we're already doing, basically building the model to represent processes and feedbacks, and using the model to generate predictions or projections. The top 3 layers of the pyramid are things that I think we could do more effectively. And in particular, I think they would enable us to engage in actionable research in the context of climate mitigation. I come to this question with a sense of urgency. We're familiar, I think, with seeing images like this, flooding in British Columbia, or droughts in Brazil, catastrophic wildfires in California, or the intersection of poverty and climate extremes in South Asia. This leaves me with a sense of urgency to engage in climate mitigation. Net zero is a framework that has been proposed for climate mitigation that entails both reductions in emissions and the direct removal from CO2 from the atmosphere, either via direct air capture, for instance, or stimulation of natural sinks. So, what do we need to do to engage in this space? Well, I think data assimilation is an essential tool, and data assimilation has the ability to generate model states that are maximally consistent with observations, as well as provide parameter estimation as estimates of parameters. What might we use data assimilation coupled to an Earth system model for? Well, one thing is to be able to do detection and attribution of variations in the carbon cycle. Here's a picture from the Global Carbon Project showing the time evolution of the ocean carbon sink from both PCO2-based observations as well as a collection of models. And you can see that the spread across these various estimates at the end of the record, for example, is quite large, it's order of petagram. Another example in this space is encapsulated by this figure here, provided to me by Britt Stevens. This shows the northern extratropical land flux as inferred from a collection of inversion models, and you can see a comparable level of uncertainty across these projects. The critical point here is that this uncertainty is large relative to the policy framework as enshrined in the Paris Accord, and you can see on the figure on the right that Britt has illustrated that uncertainty in the context of the 2030 intended commitments. So the implication here is that we will not be able to tell you whether the Paris Accord has had an effect on the basis of bottom-up estimates of the carbon cycle. Ideas for making progress in this space include this one that we're proposing here. This is an aircraft campaign that Britt for which we're aiming to get funding, and entails repeat transects using the NCAR G5 over the North Pacific sector. The idea here is to generate, to use these aircraft observations in concert with the Earth system model, CESM, and data assimilation to improve estimates of the state of the carbon cycle, its temporal evolution, and our ability to effectively represent it. Okay, finally, a few words on engaging in proactive carbon management. Many of us are probably already aware of the various technologies that have been proposed to stimulate negative emissions here, both on land, but here I'm illustrating those in the ocean. A critical problem in this space is that right now the private sector is spinning up with technologies and real projects are purporting to sequester CO2, but the research community really needs to engage to ensure that these technologies are safe and effective. So here's an illustration, a schematic diagram of how we might leverage a modeling framework to help provide a backbone system for CDR verification. And finally, just a few words on some thoughts that were not encapsulated in that pyramid, but I was really impressed with Rob Jackson's talk on Monday and his focus on methane. I'm not aware of a collective effort on the methane cycle in CESM, but it seems like it could be really important. And then over the past several years, I've been impressed at the degree to which doing simple things with the big data outputs that we generate with the Earth system model is complicated. And I'd just like to point to this collection of efforts with which I personally am involved that are aiming to develop progress on this. I think developing more collaborative, more collaboration centered on sort of the analysis piece of our research pipeline is critical to enable us to more effectively address questions in the actionable science domain. So with that, I thank you for your attention, and we'll leave you with this diagram. I hope the conversation, the discussion is stimulating. I apologize again for not being able to participate.
All right, great. So I think we'll return to Jinji's talk now and won't have questions about these speed strategy talks because we'll be doing that in the breakout afterwards. So Jinji, I can go ahead and share my screen and you can, hopefully this will work. All right, can folks?
Yes, I can see the screen.
Okay, great. So just let me know when to switch. And as I mentioned, we're very happy to welcome Jinji Liu for our keynote from JPL to talk about understanding terrestrial biogeochemical processes with remote sensing observations and modeling. So I'll let you know also when you're at 12 minutes.
Okay, thank you so much. I apologize for the technical difficulties. I also first want to acknowledge the contribution from my collaborators, including Paul Wimberg from Caltech, Sean and Anthony from GPL. So in this talk, I will just highlight two studies that use cell observation and modeling to try to understand the terrestrial biogeochemical processes. And I will end with some thoughts of the future directions. Next slide, please. So the terrestrial biosphere, next slide, please. So sorry about the top left panel shows the terrestrial biosphere really plays a very important role in the global carbon cycle. I mean, it offsets more than a quarter of the fossil emissions so far. So at the future, atmospheric CO2 growth is a net effect between human emissions and natural carbon source and sinks. So the remaining carbon budget, the amount of carbon that could still be released into the atmosphere, critically depends on the changing of the land and ocean carbon sink. But the model projections still have very large uncertainties. The CESM model could not even agree with the sign of the carbon stock change over most of the tropical region. Next slide, please. So the large model uncertainties really could be primarily contribute to two factors: the complex processes that control carbon source and sinks, and also limited observations that have been used broadly in evaluating or improving the models. So the process that control the carbon source and sink could really span several orders of magnitude in time pro duration and also spatial scales. Some processes occur over decades, such as the permafrost thaw, and we just don't have such a long-term observation to understand these processes. And the flux stand observation that could constrain the carbon balance, but it has really limited observation over the region where have a very large uncertainty. And the greenness observation that has been available for several decades really play a very important role to improve the carbon cycle, but it's not sufficient to constrain the carbon balance across the globe. Next slide, please. The increasing cell observation provide opportunity for us to constrain the global carbon balance and improve the understanding of the coupling between the terrestrial biogeochemical processes and climate. So the left panel is a plot from a paper led by Dave Schimmel. So he dubbed the broad cell observation that measured carbon fluxes process as flux tower in the sky. So with the broad cell observation, we can constrain the net ecosystem carbon balance. The column CO2 observation from OCO2 provide global coverage in combination with surface observation and the inversion of framework. We can estimate source and sinks across the globe. So this plot was generated by the bottom right panel was generated by OCO science team. So it shows where the carbon has been absorbed from the atmosphere, where the carbon has been released. It also estimates uncertainties as well. The top-down fluxes has a footprint about 100 kilometers is instead of few square kilometers from the flux night observation. Next slide, please. Satellite observation also provide constraint on the component fluxes to close carbon budget. So with satellite observation, we could estimate GPP using the new, not very new now, solar-induced chlorophyll fluorescence observation. The safe observation is a byproduct of photosynthesis. So it has been shown it's linearly related to GPP on monthly aggregate scale, but it's really active research how to best use this observation. And with column C observation, we could constrain the biomass burning. And at the same time, with active LiDAR and radar observation, we could estimate above and below ground biomass. So with all these observations from different sources, we could constrain the global carbon balance and also could calculate some really critical quantities such as carbon use efficiency, water use efficiency, and light use efficiency. So in the rest of the talk, I will just focus on the 2 studies we have done in GPL to highlight the method we are using to use these observations to improve our understanding of biogeochemical processes. So the first, in the first study, we tried to address how much enhanced growth and greening trend over northern high latitude forests could be attributed to warming. The northern high latitude has experienced the fastest warming across compared to the rest of the globe, and also experiencing a greening trend over most of the region. But the models attribute most of these changes to the CO2 fertilization effect. So in the next slide, please. So in this study, we developed an emergent relationship between observed spatial sensitivity of GPP and the greenness and with the simulated temporal trend due to temperature. So we observed that the growing season safe constrained GPP shares a similar spatial pattern with temperature as shown in this plots. In every month during the growing season, the area that has higher temperature also has higher GPP values. The next slide, please. So then we fit an exponential function between the spatial distribution of the growing season temperature and the GPP. So each point in this plot is a growing season mean GPP and the corresponding temperature at model grade. So similarly, we also fitted exponential function with Fluxcom GP product. Fluxcom is an upscaled product based on the Fluxnet observation. And the spatial gradient of temperature explains more than 60% of GPP spatial variability during the growing season. And the exponential fitting coefficient is about 0.2. Next slide, please. So similarly, we fit exponential function between the spatial distribution of leaf area index and temperature. We also see the similar strong control of temperature on the spatial distribution of the greenness, while the fitting coefficient is smaller than the fitting coefficient than GPP. So each panel in this slide shows the 3 products we used, 3 leaf area index products we used in this study. Next slide, please. So trending models, so then we compare the spatial sensitivity with trending models. The trending models really significantly underestimate the spatial sensitivity of GPP and the leaf area index to temperature. So the gray bars from A to H shows the spatial sensitivity of the trending models, either leaf area index or GPP to temperature. So it shows it has large range of the spatial sensitivity. At the same time, the width of the bar shows the R square. So the R square is smaller than the observed spatial sensitivity. And some models shows very weak sensitivity. And I highlighted here is a CLM 4.5. Compared to the observation shown in the blue bar, also has a smaller sensitivity. So the error bars in the gray from A to H represent the variability of this spatial sensitivity across 100-year simulation. It shows that even though the models has very different spatial sensitivity to temperature, if it doesn't change with time. So we expect, because this spatial sensitivity doesn't change with time, we expect that there could be some relationship between model simulated spatial sensitivity with a temporal trend due to temperature. So it turned out to be the case. So granted, if you go to the next slide, please. So in this slide, in the top panels, in the top 2 panels, it shows the relationship between the spatial sensitivity in the x-axis and the percentage change of GPP and the leaf area index due to temperature. The models that have weaker spatial sensitivity to temperature also predicts much smaller percentage change in time due to increase of temperature. So the linear relationship helps us form an emergent relationship between the spatial sensitivity and the predicted percentage change of GPP and the leaf area index due to temperature. So with this emergent relationship, we found that leaf area index increased about 18% per degree Celsius, and GPP increased about 27% per degree Celsius, which are more than 50% or 100% higher than the training model mean. So at the same time, the emergent relationship also helped us reduce the uncertainty by 70% and 24% respectively for GPP and the leaf area index. Next slide, please. So the first study, we used the emergent relationship to understand the high latitude, the warming effect on the GP and the leaf area index. In the second study, we are trying to use the data model fusion approach to address how climatic factors that drive the carbon flux intervariability vary across the tropical continents. So in many studies, as the study I cited here, treated the tropical region as a whole, but with rich spatial information provided by satellites, we could really quantify how the intervariability, how the dominant climate drivers change across the tropical continents. Next slide, please. Oh, okay. So we use, sorry, no, the previous slides. Previous slides, please. The slide before, the previous, yes, yeah. Next, sorry, cardamom slide. Cardamom slide. So we use a simplified biogeochemical model, cardamom. So it simulates the carbon fluxes, carbon allocation, and the carbon, water, and energy coupling. There are 4 live carbon pools and 2 dead carbon pools. But the unique aspect of cardamom is the data fusion framework. So it optimizes both the model parameters and the initial conditions simultaneously with a nonlinear data fusion approach. It optimizes these parameters and the initial condition at each model grade. So it ingests the top-down and B flux estimates, GPP, biomass burning, and the above-ground biomass and below-ground biomass. So all these products help constrain the parameters that control the carbon balance. It also assimilates the total water storage from grades. So it also constrain the water balance. Next slide, please.
You're at about 12 minutes. So
yeah.
If you could think about a minute wrap.
Okay. So this shows the fitting to the observations. So the fitting to the observation is really not an easy task. From this, we show, because the cardamom is a simplified model, well, the observation includes all the process that so it's fitting observation is really not an easy task. But this shows the cardamom models face observation really well for all the variables. Next slide, please. Next slide. So this highlights some parameters and initial conditions as previous slide. Estimated by the cardamom. So it shows that the parameters and the initial conditions, even though we estimate the initial condition parameter at each model grade, but the final products really resemble some of the PFD distributions. Next slide. And then we use the optimized model to sequentially replace the climate drivers with the climatology of precipitation, temperature, and radiation, and then quantify the relative contribution of each of the climate factors to the intervariability of the carbon fluxes. So the top panel shows the dominant drivers for the intervariability of GPP. It shows over the tropical forest, Amazon and Congo forest, radiation is a dominant factor, while over the mountain regions, temperature, while over the savanna and the shrubland is the precipitation. And compared to the study published like about 2 decades ago, constrained by the MODIS, they show has much smaller region that controlled by radiation. And also the temperature plays a large important role over the mountainous region. Next slide, please. So for the ecosystem respiration and the net biosphere exchange, the precipitation plays a little more important role than the radiation, and even over the tropical South America and the Congo region. So it shows like really at a great scale, the precipitation is a more important driver for the net biosphere exchange. This is really consistent with the study published in 2017 using the flux column observation, but that using the statistical approach. With the conclusion we draw from this study really is an emergent property from data constraint model. So this really implies some promise of using cell observation to improve the model prediction at a great level. Next slide, please. So this really come to the summary. So I really just talk about three points. One is about we could use the cell observation to constrain the carbon budget across the globe. I used the two studies to highlight some of the research work we are doing at GPL using either statistical emergent constraint approach or data model fusion approach to improve understanding of the biogeochemical processes. Next slide, please. So this is my final slide. Next slide. So the final slides. So I think I just one point I want to emphasize that cell observation really provide rich spatial information we could better use to constrain not only the global carbon balance, but really spatial distribution of this carbon balance. This is really critical to improve prediction, and also to increase the effort to like using the observation to constrain the model parameters and the initial condition. And the last point is really to increase the dialogue between the modeling community and observation community to better use the current and the future cell observation. Thank you so much for your attention.
Thanks, Jinji. I think we don't have time for questions, but if folks want to put them in the chat, and Jinji can try to address those in the chat.
And as a reminder, we're going to have a discussion at the end of this small session. So we'll just have 2 more short talks and then a discussion.
Yep. I think I'm up next.
Yes, I will let you know when we're at 5 minutes.
Okay, that sounds good. Let me go ahead and share my screen again. So I'm presenting just one of these quick strategy talks. I wanted to focus on how we can potentially use BGC capabilities within CESM to guide adaptation and mitigation science. So some overlaps with what Matt has discussed, but I guess I'm coming at it from the perspective that if we want to avoid catastrophic climate change, carbon is ultimately going to have a price. And I think that provides some opportunities that we can use CESM BGC capabilities to track stocks and flows of carbon, that we can use this model, which uniquely captures natural variability in the Earth system, to try to improve our capability to use observations of CO2 that Jinji discussed and Matt mentioned in his talk, to be able to sort of see the signal that's emerging due to trends in human activities and natural feedbacks rather than the variability in the system. And sort of most importantly, we should be identifying partners or stakeholders with whom we can share information and with whom we can think about how we can further develop model capacity and application of the model. And I think that ties into some of the talks that occurred yesterday in the justice session, that, you know, we've got this amazing tool and we probably need to start thinking about different ways of doing science, moving away from this CMIP perspective and towards user-driven and applications-driven focus of how to use these capabilities. So one example of how we can use our capabilities for mitigation science, we know that there's a relationship between temperature change and cumulative carbon emissions. This is a figure from Matthew's paper in 2009. And more recently, we can see on that figure that there are a lot of processes that can nudge that relationship in different directions. And many of these are related to biogeochemistry. So for instance, carbon cycle feedbacks on land and ocean, long-term permafrost feedbacks, and things like non-CO2 forcing. So methane, for instance, is an important biogeochemical compound that in the short term can really nudge us away from this single transient climate response to cumulative emissions curve and towards something higher, but it's also on an actionable basis, an area that we can have control over. And so there's a lot of ways that we can use BGC capabilities to better understand opportunities for mitigation. In terms of what we can provide for actionable carbon accounting, one of the key things that we can provide in terms of what Matt mentioned, that inverse models haven't sort of converged even over the last 30 years. CESM BGC is sort of uniquely capable of describing at a process level what drives interannual variability in carbon cycling. And if we can take advantage of that potentially in the context of data assimilation with some of the rich observations that Jinji described, we would have a much more potent way of being able to say to policymakers and decision makers, this is what we think the state of the carbon cycle is, and this is what remaining emissions are. Similarly, the work that's been going on within BGC to include riverine transport, if we can put carbon into that in a truly coupled way, we have an opportunity with this model to keep track of some of these invisible fluxes of carbon that can make carbon accounting difficult, and the uncertainties can, at a decision-making perspective, sort of overwhelm the values that policymakers want. So those are some opportunities. I think there's also opportunities with BGC to do adaptation science. The land model is making huge strides in including sort of actionable components, including agriculture and being able to model forest vulnerability and health within fates. I think we should tie some of these impacts back to carbon storage and local climate impacts in the fully coupled sense. So we're not just thinking about what's happening on land and vegetation, but what does that mean for carbon stocks? What does that mean for feedbacks with local weather due to what's happening on the land? And for this to be useful, we need to form better partnerships with communities and decision makers. So what information do they deem actionable? And can we figure out ways that we can use uncertainty in our model rather than as a hindrance, as a way that we can think with stakeholders about how to do scenario planning? How can we take our global model and move to a framework where we have multiple stakeholder groups that can use the different worlds envisioned by CESM BGC to think about what the future might hold. So those are just a few ideas about where BGC can go next. And now we will hear from Abby.
Great, thanks, Gretchen. I'm going to give another perspective on things that we can do as part of the BGC working group. And I want to start by saying this is, they very much support the ideas that have already been presented, but this is to present some additional perspective of things that I think BGC is uniquely suited to work on. So my main point is that the coupled system works differently than the individual components in isolation, and that the BGC working group is core to investigating and building understanding of this coupled system. So maybe a bit one step upstream from the application side of things, but that there's really no other place within the CESM where people are focused on why the coupling matters and how the coupling changes the answer. So I'm going to give just a couple of examples of this to motivate it. And then I'm excited to hear what other folks have to say in the discussion. So first is just to point out that when we couple land and atmosphere, we get a very different climate response to changes on the land surface. So this is a study by Marisa Legou looking at when you change land surface properties, how much temperature change do you get for making the surface darker when you have only the land model on the left, and when you couple the land model and the atmosphere model, you get a lot more response of the climate system. And so this is just an example of where we need to be thinking about changes in the climate system where we're considering all of the components and how they feed back on one another. Not only is the magnitude different, but the spatial pattern is different as well. This is to say that model choice matters. This is showing from CMIP5, the range in carbon dioxide concentrations across the fully coupled carbon cycle models. So a difference of about 300 parts per million in the atmosphere in 2100 within a single scenario. So a single emissions driven trajectory leads to a range of CO2 in the atmosphere outcomes of about 300 parts per million across models. But the parameter choices within a model also matter. This is a study by Ben Booth et al. From the Hadley Center models. This is actually going back to CMIP3, but this is an example where they took a single model and perturbed a whole bunch of parameters with the fully coupled carbon cycle model. These are variations in land parameters, and they get a range of 450 parts per million just within a single scenario, within a single model based on parameter choices. So I feel like this is an underexplored space of how we understand what the implications of our choices are in a coupled context that goes beyond just our understanding of that within a single model component. Here's an example showing that the uncertainty of the carbon cycle doesn't stay in the carbon cycle. So this is the amount of warming you get from increasing CO2 due to the radiative effects on the left, due to the physiological effects on the right. It looks small due to the plant's responses to CO2, but it is up to 20% locally of the warming, and it's even 6% in the global average just due to how the plants are responding. And again, that is going to vary across models and across parameter choices. So there is an embedded behavior of the carbon cycle in a lot of these physical climate outcomes that I think is often not considered carefully. And these plant responses are very uncertain. These physiological effects show up additionally in things like rainfall, as Gabe Cooperman showed a few years ago. So I just wanted to show you really quickly one plot we've done. This is the very first look at a perturbed parameter ensemble within not the fully coupled carbon cycle, but with land, atmosphere, and a slab ocean. We used work leveraged from Daniel Kennedy et al. Doing their land model perturbed parameter ensemble to pick 18 parameters that should influence the atmosphere. And we ran high and low values for those. It gives a range of 2.25 degrees Celsius in average land surface temperature in the pre-industrial. I'll skip over the detailed regional ones to tell you that this is being driven at the boundaries by things like the dry surface layer parameterization and biomass heat storage and stomatal conductance parameter choices. We have a lot more work to do to understand that and its spatial pattern. But I wanted to point out that this is quite a large range, even when we include the changes over ocean. So in fact, it's 1.23 degrees Celsius range across these parameter choices in global mean temperature, which is, you could compare to something like 3 degrees across all CMIP5 models. So this is quite a large range just from these parameter choices. And again, this is an illustration just of this idea that the coupled system works differently. And I think the Biogeochemistry Working Group is uniquely poised to be thinking carefully about the implications of coupling and how the individual components may be more important or important in different ways when they're coupled together. So thanks.
Great, thanks. So now we're reserving about, I think maybe we might end up eating into the break a little bit, if that's okay. We had a 20-minute break scheduled, but maybe we can move that to a 15-minute break scheduled. And then we can have like 10 minutes in breakout groups and 10 minutes to recap in a larger group to sort of discuss what areas you all find most compelling in terms of directions that we could take the BGWC. What are you interested in doing? What capabilities would you like to be added? What connections would you like to be made? And hopefully sort of a look at what the modeling efforts at JPL are, and a few visions for what we could be doing will help stimulate that discussion. So I think we've got a Google slide deck that folks can put their ideas in. I'll paste that into the chat, and then we're going to break into like, oh, Abby already did, great, thanks. We'll break into like 6 different groups, and you can have 10 minutes to brainstorm, and then we'll come back as a group and we can share a vision before we have a break. So
yeah, pick someone to report out from your group as well. So we'll hope to hear some ideas back from folks.
thanks.
Thanks. Welcome back, everyone. I hope you had a chance to have a good discussion with folks. We would love to hear out from some groups. I think I'm just going to randomly call on groups, although I don't know exactly who is in each group. So can I call on group 8 first?
Yes, you can. So my name is Jackie Schumann. I'm based here at NCAR, and someone else in my group nominated me. So I will report on our group. We feel that we should continue to leverage the work with the PPE for assimilation of remote sensing observations. With that, the connections between observations and models, focusing on how we reduce uncertainty. We've already seen examples today with the PPE and Claire Zarakis's work that there is a lot of sensitivity to parameter choice. And so there's a feeling that we should embrace uncertainty. You know, we can tune up the model, but that uncertainty is inherent to the process. And so something like fates, which adds complexity, has the capacity, it may not reduce uncertainty, but it's going to give us more information. And so that information can be more directly connected to observations, you know, outside of remote sensing, but also inherent to remote sensing. Ocean-based work, specifically ocean-based carbon dioxide removal, looking into where does this matter for policy. CESM is a key tool. It's not necessarily being used in back of the envelope calculations. And so looking at the downstream effects and global impacts as with the land or the ocean, these are not limited to specific regions. And so in the coupled framework, you know, we can see that things extend across the ocean and land respectively. And that was our quick jam session.
Awesome. Thanks, Jackie. And then since we do want to give people a time to have some break, can we just hear one comment from a couple of other groups? I'm going to nominate group 1 to give us one thing they talked about that they'd like to share.
Hello, this is Holly Olivares. Let's see, how do I pick one thing? I'm going to choose, well, what we were talking about was not particularly abandoning the CMIP process, but also not continuing to put so much weight into it as the thing. But at the same time that we can't have just one model that is shifting our priorities. So 1000% on board that we shift how we're using our tools, but that it would be great if we have more than just CESM that is doing this in this time frame. Thanks.
Super. And then I'm going to go to group 7 as our last comment.
Keith, do you want to do it or should I? I don't think we ever.
Go for it, Kristen.
Okay. So we just had our discussion more blended it into doing actionable science, like basically reevaluate which community runs could be done with be useful to stakeholders, actually, like in terms of conservation or fisheries, because it's just become clear that, you know, a lot of the potential collaborators don't even know the model runs exist and what output is actually available from them, just in terms of being useful. And we know this is like this actionable science has been a big focus here at NCAR. And yeah, making sure that we communicate these results more effectively. So I'll leave it there since we're being quick.
Okay, I actually decided we have time for one more group to hear one more comment. So how about group 6?
I can go, and I wasn't the one who came up with this. So Britt, you can chime in. But one thing that came out of our discussion was the ability to run atmospheric conversions with CESM, like inversion models with CESM output is something that we haven't had since Natalie left. That was a few years ago. So it'd be a nice capability to bring to bear.
Okay, and in our last minute, does anybody have a burning thing they wanted to share from their group that didn't get shared already? I'll ask for volunteers. Go ahead, Peter.
I was just going to say methane was something that came up in our group as being really important, especially after Monday's discussion on the importance of methane. And we don't really have a methane cycle in the model right now, which we can run interactively. So that could be an effort that we could put into for the BGC.
Great. Okay, thanks everyone. I wanted to give everyone a few minutes to take a break before we reconvene in 15 minutes. I think there's going to be breakout rooms if you'd like to stay and chat with other folks, or we will see you back here in 15 minutes for talks.
And if you are a presenter, if you
Oh,
want
yeah.
to go ahead and try sharing your screen during the break, and if you can't share your screen, like I've gotten slides from several of you, but make sure you send to either Abby or me your slides if you can't share your screen. Thank you.
I'm just going to try to see if I can share mine really quick.
Great.
And then could we get some optional breakout rooms started? That would be great.
They are open.
Excellent. Thank you. So if you want to join a breakout group, there's a breakout room button down in your toolbar.
That looks great.
Perfect. Sweet. Thank you.
Ditto, Nathan. You see me, Gretchen?
Yep, I can see you. Thanks, Nate.
Thanks.
I have to try now. Looks like that's working.
Yep.
See your desktop, but yeah. Okay, close enough. You can make it work from there.
I'll test mine.
Yeah, it'll work.
I'd like to give mine a shot. This is Amanda afterwards.
Sorry, I jumped in.
Oh, that's all right.
But it works.
Good.
You're gonna speak up and jump in whenever there's a break. Great.
So Gabe is good, and Amanda, if you want to go now.
Great.
Yep, that looks good too.
Cut down a little bit. Perfect. Thank you.
Amanda, I will say I'm sitting on Yvonne's draft right now. So
I was just gonna say
catch with you and Galen soon.
In a while, yeah. Chat it.
I'm gonna jump in next here. You see this okay?
Yep, that looks good. You see it? All right, well, hopefully everything will go more smoothly after the break, AV-wise, than before. So thanks everybody for testing that out.
Gretchen, are you ready for me to close the breakout rooms?
Yeah, I think that would be good. And we'll get started at 4:15.
Okay, they are closed.
They're still chatting away in my group, so.
Abby, do you have a idea for how to do this?
Do you like keeping time or no? We could do half and half or.
Yeah, we can do it half and half. That sounds good. So I could keep time for the first session, and you can do introductions.
Sure.
All right, sounds good.
And we'll give you a warning, Nicola, at 10 minutes or yeah. Okay.
Yeah, 10 minutes, then hopefully we'll have 2 minutes for questions.
And my introductions will be very simple because I don't have much information about folks, just their names, their titles. All right, welcome back, everyone. We are going to get started with a series of 4 talks, and then we'll have a short break, just a quick break, and then 4 more talks after that. The first group is loosely centered around ocean topics, and the second group loosely centered around land topics, but these are all things that projected onto the coupled system, and so I hope are relevant to everyone who's gathered here. First up, we have Nicola Wiseman. You want to go ahead and share your screen? And you're also muted as well.
All right.
There you go.
Just minimize that. Ooh, okay. All right. Hi, everyone. My name is Nicola Wiseman. I'm a graduate student at the University of California, Irvine, and today I'll be talking about phytoplankton variable elemental stoichiometry and how that modifies marine carbon fluxes. So let me just think. Okay, there we go. So as you know, the BGC working group, most of us know that the carbon export of the ocean is linked to nutrients via a process called stoichiometry, where in the surface ocean, we have phytoplankton undergoing photosynthesis, where they take up carbon dioxide, nitrogen, phosphorus, iron, and other micronutrients, assimilate into phytoplankton biomass at these ratios and export, where it is therefore exported to the deeper ocean. And so I'm going to be focusing on this sort of last part, this portion of the marine biological pump right here, where we have this phytoplankton biomass, where these elements are assimilated together at this ratio. So recently, what we've been doing with the CESM BEC is looking at these carbon to nitrogen ratios. So phytoplankton carbon to nitrogen ratios play a key role in the coupling of the carbon and nitrogen cycles, where there are significant variations in different ocean environments. So if I call your attention to this graphic right here from Martini et al. 2013, these are observations of particulate organic matter C to N ratios, where the blue dots, as small as they are, less than 5, and then we have them increasing towards red, where red is greater than 8 mole per mole. And observations have shown that these variations are linked to the nitrogen supply in these regions. And some other Earth system model experiments have shown that including variable C to N is necessary in order to accurately account for total C to N to P variability, as well as nutrient cycling. So what we want to know is what are the downstream effects of implementing variable C to N, and what impact does it have on the global biogeochemical cycles. So this is just some more motivation of why we need variable carbon to nitrogen models. So most Earth system models have used fixed red field C to N ratios previously, and this has been found to underestimate the ocean DIC inventory. And that as well, that the marine nitrogen cycle is more sensitive to biological processes when variable C to N is included. So the marine nitrogen cycle we care about because it's key to global net primary productivity, as most of the oceans are nitrogen limited, and perturbations to nitrogen export and nitrogen fixation affect the global nitrogen supply. And denitrification in particular, which serves as a loss of nitrogen from the marine ecosystem, is very sensitive to export and oxygen availability, which are also highly variable within Earth system models, and particularly the ocean biogeochemical models. So I'm presenting some results here using the CESM BEC version 1.98, where we have 3 phytoplankton classes, our small phytoplankton, diazotrophs, and diatoms, where we now have fully variable C to N to P to Fe to Si. This has recently been updated to have some updated iron sources, which include hydrothermal vents and bottom scavenging, in addition to the standard atmospheric deposition, sediments, and rivers. So we implemented this new sort of metric for phytoplankton stoichiometry. So I'm just going to go through this a little bit. So now for each nutrient, N, P, Fe, or Si, its ratio to carbon is calculated from this sort of schematic, where at high ambient concentrations in the surface waters of the nutrient X, the nutrient to carbon ratio is at its maximum, which we prescribe. We also prescribe this optimal X concentration, and when the nutrient concentrations fall below that value, the phytoplankton decrease their uptake of the nutrient accordingly and reduce their quotas until the minimum is reached. So this allows for fully variable C to N to P to Fe to Si. We also have some additional constraints on our P quotas and our Si quotas. For P quotas, when nitrate is particularly low, both the N and P uptake are not just the P, but the N and P uptake are reduced accordingly in order to maintain appropriate N to P values. And for Si, which is important for our diatoms, when the concentration of Si decreases, Si to carbon decreases, just as we would expect from the schematic. But we also have an iron constraint on them, where when Si is replete, but iron is low, the Si to carbon increases accordingly. So here are our new dynamic ranges that we've implemented for each phytoplankton group. So these ranges for C to N to P were constrained from the Go Ship POM observations from 5 different cruises around the globe. We also had the separate constraint on N to P of using inverse model estimates. And then the iron to carbon range was constrained by observations from Ben Twining and others in a recently submitted paper. So we tuned these parameters accordingly based on observations, as well as sort of trying to match to observed surface concentrations of nutrients from World Ocean Atlas. And as you can see, they're highly variable, they're group specific. And so what I'm going to show here is the results of comparing a 300-year constant pre-industrial CO2 run, whereas we're averaging over the last 20 years, versus one where fully fixed stoichiometry is included. So I see a C to N to P of 96 to 16 to 1, an iron to carbon of 7, and an Si to N of 1 compared to these values here. And so I'll get into those results. Here's just that POM database again really quick. So we have observations from the Atlantic Ocean, the Pacific, as well as the Indian Ocean basins. And I'm going to be comparing them to the CESM export at 100 meters. And one thing to note is just that the export at 100 meters, the POM observations include not just phytoplankton, zooplankton, but also heterotrophic bacteria and detritus that are not present in CESM. So here we just have the the carbon to nutrient concentration, or the phytoplankton / export C to N, C to P on the y-axis versus dissolved ambient nutrients on the x-axis. And this is just showing, when we have lower concentrations of nutrients, we have increased carbon to nutrient values. So our blue is our observations, our red is our export from CESM, and then our black is the CESM phytoplankton alone. So it's just, this is the main takeaway here, is just that our export is in relative agreement with our POM observations, which is good. So then we went on forward with some of the more science questions. actually, so here's just comparing those surface POM observations. So in the background here, we have the CESM output. Again, this is export at 100 meters, overlaid on the top. And these squares are the POM observations for these transects. And overall, there's sort of general agreement between the observations and the model output. Here's carbon to phosphorus. Again, we one of the really key things is we see these elevated values in the oligotrophic gyres where nutrients are limiting. And then we see lower C to P values in our upwelling regions where nutrients are in reasonable supply. And then here's our N to P as well. So one of the main takeaways from this is that getting our surface nutrient fields correct is really key to calculating or to correctly simulating our C to N to P in the surface ocean. And gradients within these nutrient distributions can cause rapid changes in C to N to P that must be resolved in order to accurately represent key nutrient cycling. So here I have some of those results from the comparison simulations, where again, we use fixed stoichiometry on one side and variable stoichiometry on the other. And these are maps of nutrient limitation, where purple is nitrogen, blue is iron, green phosphorus, yellow silicon, gray temperature, and orange represents a replete ocean. So obviously we see very strong differences here between the variable stoichiometry and the fixed stoichiometry versions, where in the fixed stoichiometry, we're seeing a transition from the N-limited ocean that we expect and that has been observed in bottle incubations, transitions primarily to a SI and P-limited ocean. We also see large increases in SI limitation where N or Fe were previously limiting. Here's the same for our small phytoplankton nutrient limitation. Again, we see an expansion of phosphorus limitation, as well as increases in our iron limitation in the surface ocean. And then for our diazotrophs, the spatial distribution doesn't change much, except that our P limitation gets much stronger. And so these observations of nutrient limitation have been sort of in general agreement with bottle experiments from the past, as well as modeling studies that have looked at these surface maps of nutrient limitation. So obviously, when we use fixed stoichiometry versus variable, we're having very direct impacts on the surface nutrient cycling, which leads me to some key global fluxes that I have here. So on carbon and nitrogen fluxes, again, we have our variable simulation versus our fixed, NPP, POC export, nitrogen fixation, and water column denitrification. So when the fixed stoichiometry is used instead of this variable, we have a decrease in all of these parameters, all of these values and fluxes. So we get a decrease in net primary productivity of about 1.4%. We have a decrease in POC export of about 16%, a decrease in nitrogen fixation of up to 40%, and a decrease in water column denitrification of 75%. And one thing to note here is that our variable case is in good agreement with previous estimates from other studies based on observations, inverse models, etc. So it's just really key to sort of point out here that our fixed version is really underestimating a lot of these carbon and nitrogen pools and fluxes. So in summary, our dynamic stoichiometry is necessary for understanding ocean biogeochemistry and our global nutrient cycles accordingly. That changing stoichiometry will modify climate change impacts through this cascade, and that we need accurate nutrient fields in order to capture observed stoichiometry. So thank you. My contact information is there, and feel free to email me if you have any questions. Thanks.
Great, thank you.
Maybe questions in the chat or one quick question as we get the next slides up.
Yeah, so why don't we go ahead and have there we go. Great job, Amanda. We'll get if somebody, I'm not seeing any immediate hands. So if you have questions for Nicola, please put them in the chat or contact her, but go ahead and have a discussion in the chat there, and we'll move on to Amanda. So Amanda Fay is up next.
Hi, everyone. Good afternoon. My name is Amanda, and I'll be presenting work today utilizing the CESM Large Ensemble to investigate the impact of Mount Pinatubo's eruption on ocean biogeochemistry. So we call it the Mount Pinatubo Gulp, and it caused immediate and long-lasting impacts on ocean oxygen and carbon. And this is work I'm doing with collaborators in NCAR, Sea Boulder, Columbia, and Scripps. So just a quick overview, large volcanic eruptions such as Pinatubo, which erupted in June of 1991, act to cool the climate due to the injection of aerosols and other particles into the stratosphere. Obviously much more complicated than that, but that's just a basic overview. So our experimental setup involved creating a new large ensemble with the sole change being the manipulation of the volcanic aerosol mass mixing ratio forcing. So we replaced the 5 years, 1991 through 1995, with 5 previous years, 1986 through 1990, to simulate a non-eruption condition. We ran this ensemble for 35 years, 1990 through 2025, and we have 29 ensemble members that we're comparing to the original CESM lens. I want to touch on another detail of the experiment though, because we actually reran the original CESM1 large ensemble on the Cheyenne machine. We found that the small changes caused by the compiler computer switch impacted our ability to do a true one-to-one comparison because we were running the no Pinatubo on Cheyenne. So the preliminary analysis I did looking at the impact of the computer change showed that the changes were on the scale of what we would see as variability within members of a large ensemble, depending on what variable you want to look at. So perhaps these 29 members could be useful to others in the community. So I wanted to just be sure and highlight that. There's 29 additional members of CESM1 large ensemble that are run on Cheyenne. So while I'm presenting results focusing on the biogeochemical variables, all model output is saved on campaign storage for 6 hourly, daily, monthly resolution. So we have a 29-member ensemble of CESM and a 29-member ensemble of CESM no Pinatubo for the years 1990 through 2025. I don't think I wrote this anywhere, but we use RCP 8.5 to extend past historical. And the results I'll show will mostly focus on the anomaly between the two ensembles. So we subtract no Pinatubo from the original lens. And we'll go through some interpretation of these plots. Just to jump right into the results, we find that the two ensembles show that the ocean's physical state and the surface fluxes respond very quickly post-eruption. And changes in the interior are long-lasting. Oxygen is immediately injected into the upper ocean post-eruption, and then it transits to depth where it permanently increases the interior ocean inventory. And the global ocean carbon sink increases by nearly 0.3 petagrams of carbon per year in 1992, so just right after the eruption. And that's a magnitude consistent with observations we see in the real world. So first, looking at the physical response, just to understand a little bit of that. On the top plot, I'm showing a sea surface temperature for the 29 ensemble members of both CESM in blue and the CESM no Pinatubo in red. And the ensemble means are the thicker lines, and the time series below shows the difference between that. So again, CESM minus the no Pinatubo. And so what we see is that this model shows a forced global SST decline of nearly 2.2 degrees Celsius immediately after the eruption. You can see it right here, and then this anomaly here. And that the individual ensemble members range in magnitude of cooling, of course, but the 1 sigma spread is about 0.08 degrees Celsius. So the cooling persists, that signal of cooling persists, and the ensembles are statistically significant out to 1996. That's that thicker line here. And I'm not including maps here, but I wanted to mention that we see that the cooling induced by Pinatubo is highly structured in space and time, and the Indian and Pacific Ocean basins are playing the key roles. We don't find any statistically significant cooling in the Southern Ocean in the simulation. Looking below the surface now, this is a cooling signal spreading deeper into depths with time from this Havmaler of the top 1 kilometer of the ocean. And again, CESM minus no Pinatubo, so the blue is showing a cooling signal. Stippling covers the areas where there is no significant difference. So at 95% confidence bounds. And blue indicates that cooling caused by the eruption of Pinatubo. And we see it significantly in that top 100 meters, but it does persist for about 5 years in that surface layer, but also a significant cooling, albeit much smaller in magnitude, persists at depth all the way through 2004 and beyond, actually. Again, we go out to 2025, but I'm limiting the time shown here just for sake of highlighting the most interesting parts. We see that after 1996, the surface kind of returns back to indistinguishable from the no Pinatubo and Pinatubo, they're oscillating here. And that signal is different if we look at depth. So now we're going to extend our view down to deeper depths, and I'm showing the ocean heat content for the ensembles. Inventory down to 1,000 meters. Again, CESM in blue and no Pinatubo in red. And you can see that the ocean heat content is significantly reduced due to the eruption in CESM. There's a large drop in the blue line ensemble here. And unlike SST, which we saw in the last slide, the ocean heat content does not rebound to no Pinatubo levels. There is a consistent difference between these two lines all the way through 2025, in fact. So the external forcing of this Pinatubo eruption is having a lasting impact on the ocean heat content in this model. Next slide. I want to reiterate that there's so much to look at. We have the full output of this model, and we've just scratched the surface. So we took a quick look at AMOC, found significant anomalies here, showing a 1995 through 1999 mean AMOC anomaly from CESM minus no Pinatubo. So this would be a strengthening of AMOC circulation for this time period in the ensemble with Pinatubo. And if you just, zoom in on the 45 degrees north here, in these time series, we're showing both ensembles and then the difference on the bottom. And this force signal is showing an increased AMOC anomaly of about 1 sphere jump, but I also plotted the 3 largest members and 3 smallest members of the 29-member ensemble. And you can see that in some members, the AMOC anomaly is as high as 5 sphere jumps. So that's something to take away. There's lots more to look at in regard to circulation and other physical variables. So I hope others are able to utilize this model. But jumping now to biogeochemical variables, time series plots of oxygen and DIC inventory on the left, and then the ensemble mean differences for various depths on the right. We'll go through it. So the left, we're looking at the top kilometer, reflecting, you can see on the top this deoxygenation trend in the global ocean. There's a clear divergence between the force signal of CESM and the no Pinatubo ensembles. The gulp of oxygen taken up by the ocean immediately following that eruption causes a temporary increase in the oxygen content, so a hiatus in that deoxygenation trend. And it's strong enough to counteract the effects of deoxygenation in the ocean through 1995, roughly. So looking at various depths on the right, you'll see that significant inventory anomalies for both the upper and deep ocean exist here for these first few years. Meaning an increased oxygen content with the eruption in the upper ocean through 1998, and impacts to the oxygen in the full depth inventory, this darkest orangish red color, extend for the entire 35 years of this experiment. So significant increase in oxygen in the ocean due to the eruption of Pinatubo. Looking at carbon now, the gulp of carbon taken up by the eruption or after the eruption amplifies the increasing carbon trend. So carbon in the ocean is an increasing trend as opposed to oxygen. We show larger DIC inventories in CESM model suite as compared to the no Pinatubo, and these anomalies are mostly pronounced in the upper ocean for carbon. You'll see not as much of a spread between these lines showing different depths. So in contrast to the oxygen inventories, which increase with the depth of integration, shown in those orange lines, the carbon anomalies are consistent across the depth, which indicates that the largest anomalies are concentrated in those upper layers and they dominate over smaller differences at depth.
You're at 10 minutes.
Excellent. Just want to touch on some other work that's being done on this project. So So these runs are being utilized by Holly Oliveres in the Lewandowski group at CU Boulder. And the question they're interested in is, what is the impact of Pinatubo in a transect framework? So specifically, the bulk of state of the ocean observations were collected in the years following the eruption with the Wills-Dragoff's effort. And so questions like, were these baseline observations impacted by the eruption that coincided with this effort? And how could that potentially change the trends and changes in ocean climate that we're interpreting from these observations collected in the early 90s? This is a quick slide of Holly's work, which I won't jump into, but she's creating a virtual transect around the ocean and can plot that transect both for CESM and no Pinatubo and look at differences. And they're finding some really cool stuff. Looking at variability, they'll also touch on CFCs and biogeochemistry trends. I'm excited to see how that work develops. So just to wrap up, we have 29 ensemble members of CESM run with a single change to the forcing to simulate a no Pinatubo world. We find that the physical state and surface fluxes respond quickly post-eruption in this model at least, and changes in the interior ocean are long lasting. If you're interested in working with these, we hope you are. Please contact Matt Long, and I'm happy to answer any questions as well. Thank you.
All right, we've got time for probably one question.
I'm also happy to answer in chat if that's easier for people.
Yeah, you're welcome to go ahead and raise your virtual hand on Zoom if you'd like to ask a question, or type it in the chat. And you're welcome to go ahead and pull up your slides while we're transitioning. All right, go ahead, Keith.
Yeah, so the extra CO2 uptake with Pinatubo, have you quantified what part of that is surface cooling and what part is stronger biological pump?
We haven't, specifically separated them, but you can see that it's not all driven by solubility. The surface temperature doesn't account for all of that change, both in time and space. So definitely some combination of the two.
Thanks.
Yeah.
Great, let's go ahead and move on to Yi. If you have other questions for Amanda, please put them in the chat. Thank you for super interesting talk. You can go ahead and share your screen when you're ready.
Okay. So can anyone see my screen?
Yes, we see the whole PowerPoint. Do you want to see if you can put it in presentation mode?
Wait,
that looks great.
Okay.
Yeah, go ahead, Yi Liu.
Thank you. So I changed a little bit of my topics. My name is Yi Liu, and I'm a PhD candidate in University of California, Irvine. And today I'm going to talk about modulating the ocean carbon sink by multiple ocean processes under climate warming. So this study is a little bit than classic CESM studies. We base on CESM circulation, and we combine this with an offline BGC model to study the effect of ocean processes on global carbon uptake. So this figure is a schematic of carbon uptake and carbon transport in the ocean by Ocean Carbon Biogeochemistry Workshop. And this figure shows that ocean plays an important role to take up anthropogenic carbon from atmosphere. And the total ocean carbon have two components. One is natural carbon and one is anthropogenic carbon. They are first driven by the rising atmospheric CO2 under climate warming, but the ocean carbon uptake is also moderated by multiple ocean processes. So as we can see from this figure, like the biological pump, which transfer carbon from surface ocean to deep ocean, could affect air CO2 flux by moderating the surface DIC. And also the circulation, here we mark as overturning circulation. The circulation can also distribute carbon in the ocean and also can affect air CO2 flux. And also the sea surface temperature, which is rising with climate warming, will also reduce the solubility of carbon from atmosphere into the ocean. And the surface wind speed, which will also affect air CO2 exchange rate. So all these processes can affect ocean carbon sink. So our question is, could that be possible to distinguish the contribution from individual ocean process on global ocean carbon uptake? So here is for our methodology. We first, based on the first version of CESM 1.0, to integrate from pre-industrial to year 2300 under the business as usual warming scenario, RCP ECP 8.5, with the resolution is around 1 degree horizontally and 10 to 250 meter vertically. So based on the CESM outputs, here we show the CESM annual global carbon uptake. So we can see the ocean carbon uptake peaks at around 5 petagram carbon per year at 2080s, and then decreases afterwards. So what we're trying to do is try to understand the contribution from each individual process that to the global carbon uptake in this figure. But to answer this question, it is hard to distinguish different processes only based on the coupled climate model. So what we are trying to do is to retrieve the CESM circulation to build up transport operator and then combine this with an offline BGC model so that we can easily separate the role of different ocean process to the carbon uptake. So here is our equation. The first C here is the is the dissolving organic carbon in the ocean, and TR here is, like what I just mentioned, the transport operator from CESM1 outputs, which include the information from both advection and diffusion. Because we have the model outputs for 450 years from pre-industrial to 2300, and we have the annual outputs. So we have 450 annual transport operator to contribute to the circulation part in the model. And then we have the biology contribution in our offline model. The biology contribution is solved from a linearized BGC model, which is not shown here. And also the other term is the air CO2 flux, which is how much carbon that ocean can take up from atmosphere. And the second equation here is the alkalinity equation. The alkalinity is also needed to solve dynamically because alkalinity plays very important role in controlling air CO2 flux. So here is our new model, and we try to set up a few sensitivity tests to understand the contribution from each ocean process. So here is our sensitivity experiment. The first one is a control experiment. That means we fixed atmospheric PCO2, we fixed biology, we fixed circulation and sea surface temperature at pre-industrial level. And I keep this as a control experiment. And for the other experiments, we try to include different terms which changes with climate. So the second experiment I call it circulation, which means I only allow circulation changing with climate. That means like the difference between the second experiment with the first experiment could show the circulation change, the impact of changing circulation on natural carbon uptake, because we do not include changing rising atmospheric PCO2. And the third experiment here is we have rising atmospheric PCO2 at RCP ECP 8.5 warming scenarios. And then we keep include a biology term, allow biology primary production and export production changing with time. And then we have another experiment. we have changing atmospheric CO2, changing biology, and also we allow changing circulation. And the last experiment is a full climate run. So the difference between the third one and the first one can give us like the contribution from atmospheric CO2 increase. And then the difference between the fourth one and the third one gives us the biology contribution. And also we can separate the contribution of circulation on both natural carbon and anthropogenic carbon. And also we can know the sea surface temperature changes on the global carbon uptake. So before I show the contribution of each ocean process, I would like to show a global pattern of air CO2 flux at pre-industrial level, or at the end of 21st century and at the end of 23rd century. So we can see the positive here means the ocean takes up CO2 from atmosphere, and negative means ocean releases CO2 from atmosphere. So at pre-industrial level, we can see the natural carbon outgassing happens at the upwelling region, and the ingassing happens at the downwelling region. And the air CO2 flux keeps increasing to the end of 21st century. But as time goes by, we can see the air CO2 fluxes keeps decreasing after 2100. This is because one is atmospheric CO2 not keeping increase so fast. And also the lower latitude surface waters might become more saturated. And now I will show you like the air CO2 flux in different sensitivity experiments. So the red line here is the ocean CO2 uptake, as we suppose the circulation and biology remain at the pre-industrial levels. That means the red line means the air CO2 flux, which we only allow atmospheric PCO2 increases with time, but we keep all the other ocean processes constant at pre-industrial level. And the blue line here is we still allow the atmospheric PCO2 increasing, but we also allow the changing circulation into the model. So we can see that the difference between the red line and the blue line shows a contribution of changing circulation to global carbon uptake. And we can see that the effect of changing circulation emerges from around like 2050 and then becomes more and more important, especially after 2100. That means like after the atmospheric CO2 doesn't keep increasing that fast.
You're at 10 minutes.
Okay, and then the pink one includes the changing of biology on the based on the blue line. So we can see that the decreased export production or export primary production will a little bit reduce the carbon uptake from atmosphere. And the black line is the full climate run. So the difference between the pink one and the black line showing the increased sea surface temperature reduce the carbon uptake. And then I try to separate the contribution from changing circulation to ocean carbon uptake. So the black line here shows the reduced carbon uptake by the changing circulation. And I separate it into the red line, which is only the natural carbon cycle, and the blue line, which is the anthropogenic carbon uptake. So we can see that the red line actually is a positive number. That means even though we have slowing overturning circulation under climate warming, it promotes ocean to sequester more carbon in the deep ocean. So we can see like from the panel here, the slowing overturning circulation sequestered more natural carbon in the deep ocean, which increased the deep ocean DIC. But the slowing overturning circulation most prevent anthropogenic carbon transporting into deep ocean. That means the surface ocean could be more easily to get saturated and prevent from absorbing more carbon from atmosphere.
You're going to need to wrap up. Thanks.
Yeah. So that's almost everything I have, and there are some take-home messages. And so I just want to mention that the slowing of overturn circulation is very important in modulating carbon uptake, which is not negligible role. Yeah, that's everything. Thank you.
Great, thank you. Let's see. If Yasir wants to go ahead and pull up slides, we could take one quick question in the interim. Otherwise, we can have questions in the chat. I'm not seeing any hands up, so let's go ahead and move on to our next talk. And if you have questions for Yi, please put them in the chat and we can have a discussion there. So go ahead.
Can you hear me okay, Abby?
Yes, you sound good, and I see your slides up, ready to go.
Awesome. Hi, everyone. Yeah, so this is essentially work done with the new eddy resolving capabilities of CSM with ocean biogeochemistry turned on. And the main question that I'll be exploring today is what controls the oxygen budget in the upper equatorial Pacific. And two key points is that eddies are important, turbulent mixing is also important in this region. Some collaborators that I am very grateful for, as well as NSF and computing support by NCAR. So this work is motivated by the fact that the global oxygen inventory has been declining in the last few decades. We don't fully understand why. We know that ocean warming is expected to reduce the oxygen content due to gas solubility dependence on temperature and the dependence of stratification and ventilation on temperature. But in the equatorial Pacific, where most of the oxygen or substantial portion of the oxygen loss is happening, we don't fully understand the dynamics there well, especially since the models don't really reproduce that oxygen loss in the equatorial Pacific. And we know that the models, including CSM, do a pretty bad job with representing oxygen in this region, as shown by the lack of agreements or lack of stippling here in the models to the right that show that different models do different things depending on their biases and the processes they might be resolving. So in this work, we are considering something more fundamental, which is really what physical processes balance oxygen consumption in the upper equatorial Pacific. Because we don't have enough observations to constrain the oxygen budget, we started looking at an eddy resolving model with the idea that eddies and maybe better representation of mixing might be important in this region. And we're also interested in mechanisms and pathways of oxygen supply in this region and how they might contribute to the seasonal cycle. So we used the CSM at 1/10 of a degree, coupled to BEC for biogeochemistry. And we started with a 5-year annual cycle core force simulation. This is spun up for 15 years for physics and only a year for BGC. So it's not ideal for understanding processes like what's driving the biases, but the physics is operating on BGC that resembles observations. We also do some Lagrangian particle tracking with these eddies in the equatorial region with the 3D velocity field for CSM to get a sense of some of the advective pathways that these eddies ventilate oxygen in this region. So the main region that we're looking at is the eastern and central equatorial Pacific. So the top left panel shows the mean oxygen distributions of the 26.2 isopycnals. You could see the OMZs extending all the way to the western Pacific in CSM, and in a tongue of oxygenated waters going all the way to the eastern Pacific. As far as we we know is mostly driven by the effective transport of oxygen to the Eastern Pacific by the equatorial current system. And the panel to the bottom left shows a section along 125 West that shows the signature of some of these advective pathways. However, we're looking here at the potential contribution of eddies and vertical mixing, given the fact that these two processes have been pretty well documented in models and observations that are having big impacts on the heat budget of the mixed layer and the upper thermocline. And essentially, how do these different processes balance the consumption of oxygen in the upper thermocline in this region? So here's some results. What I'm showing here is essentially a section between 100 West and 160 West from 0 to 500 depth. And in the x-axis, I show latitude. So essentially averaging over the eastern and central equatorial Pacific and looking at the contribution of these different processes, mean advection by the currents and upwelling, eddy advection, vertical mixing, or the oxygen flux due to vertical mixing, and sources and sinks of oxygen, essentially microbial consumption at depth and production by plankton near the surface. And what you'll note is that the consumption of oxygen in the upper thermocline, essentially in the 50 to about 300 meter depth, the decrease in oxygen due to these microbial respiration is essentially balanced by a combination of mean advection, eddy advection, and vertical mixing. So this is quite different from the idea that mean advection by the current system is balancing consumption across the upper ocean. So mixing and eddy advection likely play some key roles, at least based on these simulation and eddy resolving scales. So I'm going to go through each one of these and get an idea of some of the processes behind them. This is essentially a section along 125 West in the bottom that shows the transport in sphere drop based on ADCP data from Johnson and Strama and others that shows that the EUC, the north subsurface countercurrent, equatorial undercurrent, the subsurface countercurrent, and the north equatorial countercurrent indeed supply oxygen to the Eastern Pacific, whereas oxygen is being taken out by the south equatorial current. And we see this, the signature of these various jets into the mean advective term. So this is not news, this is great. But what's interesting is that eddy advection plays a really key role here, especially north of the equator and all the way down to 200 meter depth. And that's associated with the propagation of tropical instability vortices in the equatorial Pacific, especially north of 0 degrees along the equator. And it reflects two processes based on some Lagrangian particle simulations that we've done through this work. Eddy steering, which essentially leads to a northward or poleward advection of particles as these vortices are passing, as well as subduction down to depth of about 50 to 150 meter depth along the leading edge of these vortices. So here to the panels to the left show Lagrangian particles being fed to a passing vortex. And we see after 15 days, 30 days, some of these particles gain depth of about 50 to 100 meters as these vortices are propagating towards the west, and essentially subduct oxygen along sloping isopignals along that leading edge. The eddy steering component is essentially through the anticyclonic flow of the eddies, redistributing particles from about 0 to 2 degrees north, where the EUC passes through, all the way up to about 5 to 6 degrees north. So we could see that oxygenated waters from the equatorial undercurrents can be taken poleward and oxygenate the upper thermocline along with that. And then finally, vertical mixing is a critical component of oxygenating the upper thermocline here. And this is also tightly associated with tropical stability vortices. We see that most of the oxygen flux due to vertical mixing is associated with these cold phases of the tropical stability waves as they're passing. And that leads to an air-sea flux of oxygen, a fairly intense air-sea flux of oxygen, essentially a local annihilation of oxygen as these eddies are passing. And we could see their signature also in surface apparent oxygen utilization. So we essentially see that the thermocline thermocline waters are being exchanged along these hotspots of mixing. And this is analogous to what we see with the heat fluxes and the heat budget from models and observations. Some papers by Holmes and Thomas, and a recent paper by Deepak Shirian shows that the tropical stability waves and eddies embedded within them lead to a strong modulation of heat flux associated with a modulation of the shear between the EUC and SEC and other more complex dynamics. So, Abby, how am I doing on time? I'm confused on how long we have left.
You've got 2 more minutes, including your Q&A.
Okay, I'll wrap it up then. So finally, I just want to touch on how these different processes might be impacting the seasonal variability and maybe interannual variability. And we find that vertical mixing is quite an important component of the variability. And we see that as eddy kinetic energy increases from spring to fall, essentially the flux of oxygen due to vertical mixing is also intensified. And that's more or less in line with what we see with heat budget in the equatorial Pacific. So I've got some key points here if you want to take a screenshot for a summary, but I'd like to leave it with some questions for future work. And this is tightly related. The dynamics associated with tropical stability vortices include a lot of submesoscale processes. So it'd be interesting to see how submesoscale features like fronts along the leading edge facilitate the mixing, the subduction of oxygen and other transport processes. So with that, I've got some papers there and thank the co-authors. Yeah.
Thank you. We can take a question, and just to give everyone a heads up, the next thing coming on our agenda is a break, and we're going to reconvene for those talks at the half hour of whatever time zone you're in. So if you need to take that break now, but we can definitely take a question. And I just wanted to thank all of the speakers from this session for giving us a really nice broad look at all of the many different aspects of or some survey of the aspects important in the ocean, from the physical mixing to the assumptions about biology to the interactions with events in the atmosphere. That's really great to see the breadth of what's included in this working group. So if we have questions for Yasir, we can take those now. You can type in the chat or raise a hand.
Abby, I see. Sorry, go ahead.
Sorry, I was going to say a question about the mean. How is your mean operator defined? Does the eddy term include the seasonal cycle?
Yeah, so let's see. Can you see this okay, Frank? And everyone, sorry?
Yes.
Yeah. So I've left out a little bit of math. The eddy component is essentially calculated from the climatological monthly mean. So I have not been able to remove the rectified effects with the seasonal cycle, especially that these tropical stability waves are strongly seasonal. And especially after talking to Annalena and many others who've tried this in the past, it's much more complicated than that. So far, we've just been following the Griffiths et al. Method, where we just take the anomaly from the climatological monthly mean. I think it would be great to chat some more, especially with you and Anna, on how we can develop a method for taking the seasonality of the eddy component into account. Yeah, hopefully that answered your question.
Yeah, thanks, Yasir. Be great to talk.
Yeah. Great. And I think with that, we should give everyone a chance to have a break. We're going to have some breakout rooms right now. So if you want to try to catch one of the speakers, you can look for which breakout room they might be in. And you can go ahead and chat with folks there. We'll reconvene for our next set of talks at the half hour. So see everyone in a few minutes.
All right, should we start calling people back from the breakout rooms? It looks like they're less utilized this time than last
Yeah,
time.
and are also looking for our first speaker, which is actually going to be Song Wang.
Song,
You there?
projecting.
Great. We're seeing your screen. And now we see you.
Hello.
Yeah,
We
we're
still
still
got a couple of
working on.
minutes. So. But we'll do the time similar where Abby will let you know when you are at 10 minutes, and then you've got 2 minutes left for either Q&A or wrapping up.
Okay. Hello.
Let's wait just a moment before we get started.
Okay.
We were just making sure you were here and ready to go.
All right, so we'll be getting started in a minute. We've got 4 talks that are more focused on land biogeochemistry, but obviously ties to the coupled system. After that, after those 4 talks, we'll have some time at the end for sort of a wrap-up discussion. So it's another opportunity for folks to ask questions to any of the speakers or to follow up on any of the discussion that you had in your small groups or in the breakouts. So we'll have, the ideal is like 10 and 2 talks, 10 minutes of presentation and 2 minutes of question, but everyone please feel free to use the chat during and after the presentations. So we'll kick off with Song Wang, who will be talking about reparameterization as models move from carbon only to carbon nitrogen models. So thanks, Song.
Hello. Thank you. I will present in place of Professor Law today. My name is Sheng Wang, a PhD student in Chinese Academy of Sciences. Thanks for giving me the opportunity to share the study with you, a research about reparameterization required after model structure changed from carbon only to carbon nitrogen coupling. Terrestrial ecosystems cluster approximately 30% of human-emitted carbon and play a critical role in mitigating climate change, and the terrestrial carbon cycle is strongly regulated by nitrogen availability. In ecosystem, nitrogen can regulate the carbon cycle mainly by these 3 weeks. The formation of organic matter requires a certain amount of nitrogen in combination with processes of plant carbon assimilation, and the photosynthetic capacity is tightly related to the leaf nitrogen content, and the conversion and the distribution of dry matter in terrestrial ecosystem are also accompanied by strongly coupled carbon and nitrogen processes. Hence, there is a growing awareness that the terrestrial nitrogen cycle is crucial to accurately predict the carbon cycle by LCSM models and the different climate change scenarios. And more LCSM models account for nitrogen dynamic. Here is the models in CMIP6. We can see that more than half of the LCSM models have incorporated the nitrogen cycle. To achieve this carbon nitrogen interactions, LCSM models could control the photosynthesis processes by the nitrogen content, and can also control the formation and decomposition of biomass later or soil by their serum ratios. As a result, in almost all LCSM models, considering nitrogen limitation will reduce the GPP and its carbon storage without nitrogen coupling. Ecosystem carbon only model would overestimate the ecosystem carbon input and the sequestration, because the potential nitrogen limitation is not considered. It sounds reasonable, right? However, the carbon storage in the real world ecosystem will not change according to whether or not a model considers nitrogen processes. The carbon and nitrogen interactions always exist in the real world. In other words, the observations are stable no matter whether there is nutrient limiting. But for the model, in order to better simulation and prediction, most models will tune its parameter based on the observations. We know that data simulation can estimate the model parameters and reduce the model uncertainty, and it can also help model to describe the properties of ecosystem through parameter. And the ecosystem have its specific characteristics like carbon flux size, ecosystem structure, model size, nutrient condition, and so on. We can observe some characteristics with many methods like field experiment, incubation, flux observations, and acetylology. And then we can transfer this information to model for model construction. Then in return, the model is used to describe the function of the system. If the model obtains the information of the ecosystem by parameter after data simulation, the model can will simulate and predict the function of the corresponding system, and the parameter in the model will contain the information from of the ecosystem. For example, when data simulation is used to estimate the parameter in a carbon-only model, the nitrogen-related information contained in the observations is implicitly represented
We lost your
in the
slides there. Do you want to reshare your slides again, or present them?
Okay.
Your screen is on, but we're on the title slide.
They were working though.
Okay, I will re-present this slide. For example, when data simulation is used to estimate parameter in a carbon-only model, the nitrogen-related information contained in the observations is implicitly represented in estimated parameters. However,
it's still not working. Do you want to try one more time?
Oh, sorry. And
to present,
yeah. Yeah.
Or at least scroll to the right slide, yeah, then we can see. There we go.
Good.
Great.
Now it's work.
Thank you.
Okay. Oh, for example, when data simulation is used to estimate the parameters in a carbon-only model, the nitrogen-related information contained in the observations is implicitly represented in estimated parameters. However, when a carbon and nitrogen coupling model is calibrated using the same observations, the nitrogen-related information is no longer implicitly represented in the carbon-related parameter. Actually, it was reflected on the carbon and nitrogen interactions in the model. Here come the questions. If we use the same observations to calibrate two models with this simulations, what are the parameter estimation in different models? Which simulation is more close to observations? And how do model structure influence parameter retrieval between carbon and nitrogen coupling model? In order to answer these questions, we conduct research using data simulation to estimate parameters of a carbon-only model and a carbon-nitrogen coupling model based on a field experiment in Qinghai Tibet Plateau. The estimated parameters were used in their respective model to simulate carbon and nitrogen dynamics during the experimental period. Here are the main results of the parameterization by data simulations. When found that adding the nitrogen module increase the carbon exist rate of most carbon pool. It's a little different from what we know before. Usually we think that nitrogen limitation will decrease exist rate. So why we get the opposite result? I want to use a comparison to explain this result in the traditional SSM models. We think that the nitrogen limitation information degree in the carbon and nitrogen coupling model is larger than the carbon-only model. I show this relationship by the balance tilted towards the carbon and nitrogen coupling model. This relationship leads to the carbon simulation of the carbon-only model larger than the coupling model. But when we use two models to do these simulations with the same observations, the nitrogen limitation information are same in two models, but the limitation information were transferred from the carbon-related parameter in the carbon-only model to the model structure in the coupling model. When the nitrogen cycle is incorporated, and the simulation of two models should be similar or not. So what is the real result? In the experimental period, two models both will, we can see that in the experimental period, two models both will simulate the most existing pool in comparison with the observations in ambient and warming treatment. The red line is the pool size simulated by the carbon-only model, and the green line is the pool size simulated by the coupling model. That means the simulation of both models were consistent, although their model structure were different. Let's sort out the results. With the same observation data and different model structure, the constraint parameters are different, but if we use the corresponding parameter as models, the simulation results are similar. But if we use the parameter without returned by data simulation, when we incorporate the nitrogen cycle to the model, the ecosystem carbon storage will be underestimated. And here are some take-home messages. Based on this result, we get concept figures. The x-axis is the nitrogen limitation degree of the observations, and the y-axis is
you're at 10 minutes.
Okay.
Just letting you know you're at 10 minutes.
Okay. The blue line is simulation of the carbon-only and carbon-nitrogen coupling after data simulation, and the orange line is the simulation of coupling model without reparameterizations. If there is no nitrogen limitation, okay, all simulations are same. But if there is nitrogen limitation, in the observations, the system carbon storage simulated by the coupling model without reparameterization were much lower than the model with data simulation. Hence, the system models may underestimate both future terrestrial carbon sequestration and the potential carbon climate feedback, because they overcount the nitrogen constraint, and we highlight the necessity to reparameterization after model structure change from the carbon only to the carbon and nitrogen coupling. However, the carbon only model cannot capture the change of nitrogen limitation information because the nitrogen processes are not explicitly simulated by the carbon only model, but the coupling model may be better. Yes, when affirm the significance of the carbon and nitrogen coupling model. Thanks for your attention. That's all.
Great, thank you so much. We could take one quick question, or go ahead and type questions in the chat as well.
Yeah, and Nate, you can start putting up your slides, please.
Okay. Can I see my screen?
Yeah, we need you to stop sharing your screen, Song.
Yeah. Can you see my screen?
Yeah, can you stop sharing so our next speaker?
Okay.
Now you're off. Great.
Yes.
All right, so feel free to put questions for Song in the chat, and we'll get started with our next talk from Nathan Collier on scoring changes in the ILAM system.
Hello, thanks for having me today. It's a presentation about these proposed changes we're looking for feedback with. But before I get into that, I just wanted to talk just for a second about what ILAM is. I realize that a lot of new people have come to this meeting, and we used to talk about this a great deal. And ILAM also is one of those acronyms in the DOE system that becomes kind of overloaded, and you hear it to mean a lot of things. So, people could be talking about, it stands for International Land Model Benchmarking. And when they could be talking about the community, group of scientists enthusiastic about model benchmarking, of which you can be a part if you would like. It could be talking about the results that we catalog. I have a bunch listed here. There'll be a link at the end of my presentation if you want to grab the slides and go explore the links. One of those appeared in the AR6 chapter. It was in one of the slides earlier in this session. It could be talking about our software package. It's hosted at GitHub. You can install it with Conda, and a new version has been under development for a while, slowly by me using X-Ray. We're hoping that will kind of enable new kinds of comparisons, things the community has wanted. Or you could be talking about our data sets. I'm aware that there's a lot of people in this community that use these data sets because they're formatted in a very convenient way, and a large collection of quantities that are relevant for the modeling that we do. In that vein, we have a lot of new additions. There's a biomass data set from the European Space Agency that's in there that I coarsened out, that's available, and some NASA-funded weekend data that's available. The class data set, these are unique collection of a blending of a lot of products, but they provide uncertainty estimates, and they also close the mass and energy budget, which is fairly unique. I'm not aware of anything else that does that. We got T's biological nitrogen fixation in there, as well as a surface soil moisture product from a publication by Wang and Mao. So you can see those results if you go to the CMIP6 link here and check it out. And I will say, that if you would like to make contributions, a lot of those data sets that we added came from suggestions here. I think Will at least suggested 2 of them. And we like suggestions. You can email them to me, or you can go to this GitHub repository and make and open an issue with this suggestion link to what the data is. And we're trying to be a little more transparent using GitHub projects about where we are in that process. But you could also be talking about, when you say ILAM, the methodology that we have. And that's what this talk is really meant to be, is to point out some consequences of a lot of the decisions that we've made and suggest maybe a potential change to plug some holes in that methodology. So I've shown this slide a bunch of times before, but this is how we score our bias. We make essentially kind of 3 choices here. And the first is to normalize the absolute value of the bias by the standard deviation of the reference. That'll come back in just a moment. And we then map that to the unit interval using an exponential. It's a fairly standard thing to do. And then we integrate over the globe, but we integrate by a weight. And that weight is the so-called mass of the quantity there, which is, in this case, is just shown as like the mean of the reference variable. So why are we doing this? Well, whenever you construct a relative error in this way, you could have a signal that has very little noise and variability, and you end up getting a relative error that's very large, even though that really is measuring more of noise, kind of like GPP over deserts is the thing we usually use. And so by weighting then this integral for the score by the mass, we kind of filter out that. So what we found is these choices have an impact on our scores, and one that was maybe unexpected. So what you're seeing here is a distribution of biases from the CMIP 5 and 6 set of models with respect to GPP from Fluxcom. A lot of what I'm going to show you is GPP from Fluxcom. And I'm showing you these kind of violin plots and splitting it all out in different regions, which correlate to Whittaker biomes, the regions that geographical regions we constructed from the parameter space and backing out the latitudes and longitudes. So you also notice that each of those violin plots has a black dot associated with it. And what that black dot represents is the standard deviation that we're normalizing those errors by in the previous slide. And so the one I want you to focus on is the gray one, which corresponds to tropical rainforests. And notice that those dots are very close together, or put it another way, that the large amount of the biases from models in that region are going to map to scores which are really poor. So if you kind of compare the distribution of scores in these regions, you'll see that they're pretty evenly distributed except tropical rainforests. And that's because the variability in the rainforest is relatively low. It's just GPP is always on. And therefore it doesn't, and we get this kind of different effect here, and the scores from the tropics are just poor. The second effect is this mass weighting that we use. And so what I've done here is if you take kind of the full contribution, if you try to make a plot of how each pixel contributes to the overall score. So this plot down here in the bottom left is showing the area of every cell and its GPP divided through by the total sum. And what it gives you, what it shows you is that these areas in yellow in the tropics are 100 or 10 times more influential than any other grid cell in the globe. And if you take them, if you integrate over the tropics, you'll see that that's really true, right? And so this mass weighting has an effect of making our scores be highly tropical emphasized. And you can see that in the right plot, which are all of our scores. The x-axis is the global score, and then the y-axis is the score just over the tropics for all of our data sets and all of the models. It's colored there by the kind of variable or the section in our comparison that's there. And you can see that while it's not always true, they are. It is true that a lot of tropics scores are very similar to our global scores, implying that this is a problem beyond just GPP. So what's the proposed change? Well, what we're trying to do by normalizing these errors is we're trying to make the errors somehow commensurate globally. But of course, like we're picking, the globe is a very different place. As you go across biome, across latitude, there's a lot of changes. So what we're going to suggest is to capture those changes by instead looking to score in the set of biome-like regions. Here I'm using these Whittaker regions. You could pick Köppen climate regions. You could pick anything, but the main idea that I'm putting forward here is we want to pick regions inside which the errors that you can see are commensurate in order of magnitude. And so because these regions reflect biomes where the climate is similar and the vegetation perhaps is similar, then we're going to say, okay, inside this region, these errors can be treated as commensurate. And so then what I do is for every region and every variable and across a selection of models, in this case, the 5 versus 6 subset, I'm going to compute the 98th percentile, the absolute value of the bias. You could say the worst value of the bias. 98th percentile is just meant to kind of make sure we skip over any kind of anomaly or something. Essentially, what I'm asking is, how bad have the errors been, across these last 10 years of modeling that we put forward? And then you can compute a score by simply taking 1 minus the absolute value of the bias normalized by this regional 98th percentile variable. And then we can compute an overall score by integrating globally without any kind of mass weighting. And so this is a way to treat errors locally by their regions without needing to normalize by this variability, which is causing us some problems. So how does it look? Again, for GPP and FluxCom, the 98th percentile of biases I'm showing in the top left panel. And it does what you would expect, large biases in the tropics that taper off as you go to higher latitudes. And then on the top right figure is CESM2's GPP bias. And you can see our old bias score map down here on the bottom left. And maybe people haven't stared at those very much, but for like Dave Lawrence and many of the CLM group that have, you'll notice that a lot of times those maps aren't terribly helpful. They're just, they get very poor scores in a lot of regions. You can see why we were mass weighting like these dry regions in Australia, or even in the West here, where maybe there's not so much GPP. You're getting very bad scores in regions that don't matter so much. Whereas the new way we're scoring the bias really takes care of a lot of that problem and leads to a bias score, which has much better correspondence with the bias. When I glance up at the bias and look at this score, I feel there's a better correspondence. And it also highlights, for example, where the bias is anomalously different. So if you look at CESM2's high latitude GPP bias, you'll notice there's this high bias and up in these high latitudes, which is anomalous. It's different than CESM1 and with respect to a lot of other models too in the collection. And so this way of defining errors now kind of highlights that and makes these maps much more useful to kind of tease out, well, where really are we seeing the problem areas? So that's
10 minutes.
Okay, thank you. So that's our proposal. And it's kind of a rethinking of how we could approach scoring. It removes this normalization by variability, exponential mapping, mass weighting, a lot of things which were kind of necessary, but subjective decisions that we made. And it leads to a better bias to score correspondence and gives some context to our scores. Because now if you got a poor score, it means that your score is low relative to what models have been able to do, for the last, 10 years or so. So of course, there's a lot of caveats. Maybe we haven't thought through of everything. So we're welcoming some comments either now or later. The slides are there. And thank you for your attention.
All right, thanks. If folks have questions, please put them in the chat. Gabe, if you want to start putting your slides up, or if anybody has a quick question, you can feel free to ask Nate directly while Gabe gets the slides up. All right. Well, I know that the ILAM folks love to get feedback, so if anyone has any thoughts about this, I'm sure Nate would like to hear them afterwards. All right, so now we'll turn to Gabe Cooperman, who's going to be talking about competing influences on evapotranspiration and how they modulate vegetation climate impacts in the CESM C4 MIP simulations.
Thanks. Yeah, I'm Gabe Cooperman from the University of Georgia. And I wanted to share, maybe some somewhat preliminary results where we have been revisiting some of the vegetation climate impacts that were identified in CSM1 and other CMET5 models using CSM2, and sort of unfolding some of the competing influences of plants on evapotranspiration. And I thought that would be useful to highlight to this group as motivating how important plants are for the climate change signal that we're seeing in fully coupled simulations. This is work that is being led by my graduate students, Ashley Cornish and Alana Kordak, who are supported by a DOE RGMA project that's led by Abby Swan and others. And so broadly, we're interested in how CO2 affects the climate system. And so we have radiative warming that comes with a host of climate impacts that have consequences for ecosystems. But ecosystems don't sort of respond passively to these climate changes. They're integral to the changes themselves. And there's been work that has showed how plants influence precipitation patterns, flooding, drought, and heat waves in response to rising CO2. And largely that's through their influence on evapotranspiration through a couple of mechanisms. One is reducing stomatal conductance. So stomata don't open as much under higher CO2 conditions, and that reduces transpiration rates. Another mechanism is through increases in leaf area and CO2 fertilization that affect plant growth. And that can affect the surface albedo, it can affect transpiration, it can affect how much rainwater is intercepted by the canopy and then re-evaporated into the atmosphere. And in CSM1, the stomatal conductance effect was the largest, and so that led to a broad decrease in total evapotranspiration due to plants responding, in this case, to 4 times CO2. And so that means less moisture going to the atmosphere, which can affect precipitation, means more water staying in the soil that can affect soil moisture and runoff conditions. It also shifts the surface energy balance from latent heating towards sensible heating and warming that can warm the atmosphere, and it can also influence atmospheric circulation in ways that affect moisture transport and subsequently precipitation as well. And so we've been separating these plant effects from radiatively driven greenhouse effects using these idealized CO2 only simulations as part of C4MEP, where you independently control the CO2 concentration in the atmosphere and the surface components of the model. In this case, we're looking at CLM. And so I'm going to show you some results from 3 simulations. A full simulation where CO2 is increased from pre-industrial to 4 times CO2 in both the atmosphere and the land surface. A simulation called radiation, where we just increase it or it's just increase in the atmosphere, and a physiology simulation where it only increases in the land surface. And again, using these simulations, we can see contributions from both radiation and physiology to a lot of large-scale climate changes. This is showing the pattern of precipitation change at the end of these simulations relative to pre-industrial. And the 4 times CO2 full simulation on the left, that pattern looks really similar to the RCP 8.5 results. And you see sort of large increases over most of the tropics except for the Amazon. And that has contributions from both physiology and radiation. In particular, South America and the maritime continent have a strong physiology contribution. And if you take these, the runoff from these models and you downscale it for flood statistics, this is showing the 100-year flood return period changing as a result of CO2 increases. You see strong plant effects due to physiology and radiation as well. And so we can see, these blue colors in the full simulation representing about 25 or 50-year return periods from what used to be a 100-year return period, and big contributions from physiology and radiation. In some places one dominates and in some places they amplify one another. Likewise, when you look at drought metrics that take the surface conditions into account, like precipitation minus evaporation, you see a mitigating effect of plant responses relative to the radiative responses, kind of reducing drought stress in the full simulation that you wouldn't see if you looked at something like the Palmer Drought Index or something that took more atmospheric focused metrics. And then we also see plant influences on heat wave statistics. So this is looking at the heat wave total number of days and intensity. This is showing the ratio of the physiological driven changes to the radiative driven changes. And so you can see with the positive numbers that the physiology is amplifying the radiatively driven changes. And in some local regions, as much as 20 to 40%. So a significant contribution due to physiological changes. But when we compare, those results are from CESM1 and CMIP5 models. And when we look at CSM2, we see a much smaller responses. So this is looking at the total evaporation change in CSM1 and CSM2, and you can see it's much smaller in CSM2. And that means the climate impacts are also smaller. So this is the pattern of precipitation change, which is much weaker in CSM2 than it was previously. The runoff pattern is similar, but again, it's much weaker in CSM2. And this has consequences for drought and flooding conditions. And changes in temperature increase in both versions of the model almost everywhere, but those big hotspots in South America and North America and some of the high latitudes are much smaller in CSM2 than they were in CSM1. And so these are just climatological changes, the first 20 years versus the last 20 years of these simulations. But I think they capture a lot of the signal you would see if you looked at some of those higher level statistics of flooding and heat waves. And so we want to sort of, as an initial step, kind of parse out what's driving these changes in evaporation. So we looked at the components of evaporation. So starting with transpiration changes in the bottom here, pre-industrial values in the top, and then the global mean changes on the right. And you can see the CSM1 has higher transpiration rates, in part due to more precipitation in this version of the model when run it as a coupled model. But the declines are actually pretty similar in both model versions. In fact, in some regions and in the global mean, the CSM2 declines are larger than the CSM1 declines. For the second largest component to evapotranspiration, soil evaporation, Again, we see CSM1 had a larger soil evaporation and CSM2, again, related to precipitation differences, but both models had very little sensitivity to CO2 changes. Where they really differed was this third component, the canopy evaporation change, where there's a significant increase in CSM2 and very little change in CSM1. And so in CSM2, the canopy evaporation is offsetting the declines in transpiration, and so the overall ET change is much smaller because of that. And this results in part due to a much stronger increase in leaf area in response to increasing CO2. So again, the plot on the right is the global mean, and you can see that blue line for CSM2 is much steeper than the green line for CSM1. There was higher LAI in the pre-industrial climate in CSM1, but by the end of the simulation, there's higher LAI in CSM2. And so that means more rainwater can be collected onto the leaves and re-evaporated into the atmosphere more easily. And so that contributes to the canopy evaporation changes. What you also see here is, like, so if you look at the gray area, that's kind of the present day range of CO2 concentrations. And that's really where the model is. Two model versions are really far apart on what they're predicting for LAI. That's not necessarily true for other variables of carbon uptake. This is the NBP change. They're more similar early on in the simulation, and they have a much stronger sensitivity in CSM2 that leads to big changes going forward. And there's similar patterns for GPP and total carbon storage, where they're more similar kind of at the beginning of the simulation and then diverge. But leaf area in particular is not sort of well constrained for the present day range here. So I'll just kind of conclude with some main points and some questions. So we looked at these competing influences on evapotranspiration. We found that in CSM1, it's really just transpiration that's changing and not canopy evaporation. So we had strong climate impacts, but with this cancellation effect in CSM2, the climate impacts were much smaller. Some previous studies have treated these two components together, so combining transpiration and canopy evaporation as the full plant response, which has some use, but I think it kind of would lead you to believe plants are not as sensitive to the CO2 changes in CSM2. When in fact, when you unfold these individual components, you see a much stronger sensitivity to CO2 in the new version of the model. Another question that came out of this work is this amplified effect of canopy evaporation, in part at least, an artifact of weak rainfall in CAM? So we see canopy evaporation is very sensitive to leaf area changes, but we also know that CAM and most Earth system models rain kind of too weakly and too frequently compared to observations. And so does that allow for an unrealistically large control of leaf area? Like, too much water can collect on these leaves and then re-evaporate because it's raining so weakly. And the other thing with this finds is, we see differences in both the sort of pre-industrial and present day LAI distributions, as well as the sensitivity. And so there's a need to sort of understand what's driving those differences. Is it different sensitivities in terms of total overall productivity? Is the initial density in the pre-industrial climate allowing for more plant and leaf area growth in response to higher CO2 and more carbon allocation to leaves? And these are some things that would be good to constrain to understand their influence on climate. So I'll stop there, and I'd be happy to take questions or in chat offline.
Great. Thanks so much, Gabe. It looks like Dave Lawrence has a question.
Yeah, great talk, Gabe. And I think, it's so hard to compare CSM1 and CSM2 because CLM is so different in so many ways. And so you're uncovering that. You could come up with a million reasons, including the fact that in that last slide, canopy evaporation parameterization is totally different, in addition to the leaf area index having a different response. So I'm sure you've already made this connection, but I think if we get to the stage with the parameter perturbation experiment, where we do run a large ensemble of CLM5 simulations with different valid parameter sets, I think that was going to be a really rich resource to evaluate this kind of thing, with a lot less of that, like, everything changed kind of aspect to it.
So yeah, I agree.
It's
so hard to isolate what's going on. Yeah, and sensitivity experiments with holding leaf area fixed and allowing everything else to change, I think will also help unfold some of that.
You muted, Gretchen.
Oh, sorry. Yes, Dave Lawrence is going to be our last talk of the session. He's going to be talking about bioenergy expansion. You can see your slides. Hopefully he's not muted. Thanks for closing out our session. We'll have some discussion following.
Great, okay. So thanks, yeah, so I'm going to present this work about bioenergy expansion versus or afforestation mitigation scenarios. I'm representing or I'm doing with Yan Chang, who's at the, you've probably seen her talk at the Land Model Working Group or Biogeochemistry Working Groups before. She used to be at PNNL, now she's at the National University of Singapore. And part of the reason why I'm presenting is because it's just a very large time change for her. So, the idea, and I think this work ties in well with that initial discussion we had before this session got going. So the idea here is that land-based mitigation strategies are obviously going to be required, also known as natural climate solutions, to achieve 1.5 degrees C or 2 degrees climate targets. And some sectoral analysis studies have suggested that there is, obviously potential from land-based solutions to mitigate, 10 to 15 gigatons of CO2 per year, equivalent per year by 2050, which is about 30% of the mitigation that we need to achieve a low temperature targets. And the figure on the right shows a nice paper by Stephanie Rowe that kind of catalogs the different possible methods. And really, it's in addition to reducing deforestation is a good mitigation potential. Reforestation or afforestation and bioenergy, carbon capture and storage, are the two most promising and highest mitigation potential. And these are the strategies that are also employed by IAMs to develop mitigation pathways. So we want to evaluate this within CSM2, and before we get there, we need to have bioenergy crops in CLM, and we didn't have that when we released CLM5, but Yan has introduced bioenergy crops. Obviously, traditional crops can be used as biofuel feedstocks, but really perennial grasses such as switchgrass and miscanthus are better and are what would really be used in the real world in most instances because they have higher productivity and water use efficiency, as well as lower demands from irrigation and fertilization than traditional crops. And so Yan introduced these bioenergy crops into CLM5, and so we're using that capability within this study. So, there's alternative mitigation pathways. This is the shared socioeconomic pathways concept. And within that concept, there are multiple pathways that can achieve each mitigation target. So if you're trying to get to, global warming target of less than 2 degrees C, which is roughly the RCP 2.6 category, there's different pathways that can get there. For example, the SSP1 scenario, which is shown there in the bottom left here, which has low challenges to both mitigation and adaptation. It's called colloquially known as the sustainability pathway. That's mainly an afforestation or reforestation-based pathway. It involves a decreasing population assumption and less needs for food and less meat consumption. And then there's the SSP2 pathway, which also can get to RCP 2.6. And that's known as the intermediate challenges pathway or the middle of the road. And that pathway within GCAM, at least, is mainly a bioenergy-based mitigation pathway. But there's also a growing population and rising food needs that go along with this scenario. And so we've been collaborating with GCAM group to have these scenarios run, both by the same integrated assessment model. And then Yan has processed that to turn it into land use change files that we can use within CLM. And this is what it looks like from the global integrated picture. So the SSP2 in red there is this is the change of bioenergy. So a very massive increase in the amount of bioenergy crops. Some deforestation that goes along with that to accommodate that need for bioenergy crops. Some of it is conversion of cropland or grasslands, but some of it requires forests. And there's also an increase in cropland to feed that growing population in SSP2. And then the reforestation pathway also has some bioenergy increase, so keep that in mind. But there's reforestation or afforestation, so an increase in forest area, and a decrease in cropland because there's a less population and less food needs for crops. So if you look at the spatial pattern, it's pretty complex. It's in the SSP2, there's bioenergy crops added everywhere. There's some deforestation to accommodate that bioenergy, and there's an increase in cropland in many places around the world to accommodate the needs for food. In the SSP1, there's some increased bioenergy crops. There's both reforestation and deforestation, to create new cropland in different places to accommodate some bioenergy uses. So the main point of this figure is that it's a complex set of changes, regional changes in these two different scenarios, even though we're calling them bioenergy and reforestation. So the questions we want to ask in the study are, how equivalent are these pathways from a carbon mitigation perspective when you evaluate them within CSM2? And secondarily, are there significant near-surface climate consequences associated with the different pathways? So we did a fairly simple experiment. We ran 2 sets of experiments with 3 ensemble members each from 2015 to 2100. Both of them using the exact same radiative forcing and CO2 levels from SSP1-2.6, but using the SSP1-2.6 land use scenario in one of them, which we call a reforest, and using the SSP2-2.6 land use in the other one, which we call biocrop. So here's what it looks like. The 2 pathways have similar impacts on land carbon accumulation, but they get there in different ways. And so the blue curve is here what you expect with reforestation, that in addition to CO2 fertilization, that those reforested or afforested regions are gaining carbon as we expect. And so that's showing that it's working as intended in a carbon mitigation perspective. The biocrop version scenario also gets there pretty close to the same as the reforest in terms of total amount of carbon it gets there, but it goes on a much different pathway. And that would have climate consequences, which are not captured within our set of simulations because the CO2 levels will be different, but just keep that in mind. And so why is it so different? Well, one of the reasons it's so different is that there is a lot of land use change emissions in that biocrop simulation to create all that bioenergy land area. So there's a big increase or difference in the land use change emissions. And furthermore, there would be a loss of this additional sink capacity with that deforestation. So that's a loss of a potential carbon gain. And then there's also more fire emissions that happen on that biocrop land. And that's actually mostly due to degradation-induced fires from the tropics that are coming from that deforestation. So even though you're creating more forest area in the reforested run, there's actually more fire emissions coming from the biocrop. So a complex set of responses going on. For BECCS, the fossil fuel substitution and the carbon offset and carbon capture and storage efficiency are highly uncertain. So, for bioenergy to work, you have to convert that, those crops into fuel somehow, use that fuel to power cars, to create electricity. And then you also have to have mechanisms to capture that carbon. And so there's a huge amount of uncertainty that goes on in the effectiveness of these things. This looks at these plots here show, the amount of carbon offsets from, not having to use fossil fuels and the associated uncertainty with that for these 2 different scenarios. And the uncertainty is related to the future biomass yields, which, we're not capturing all the technological advances, so we kind of that. The energy conversion technology is also affected there. And then the bottom here shows the carbon accumulation that you get from the carbon capture and storage aspect. And again, there's uncertainty there. How effective is that carbon capture and storage? Is it 80% effective, 60% effective, 90% effective? And that has different consequences. So if you kind of add all these things together and say, well, if you include all those uncertainties, this is what is a more realistic or honest assessment of the potential for the bioenergy, for the differences between these 2 scenarios. And basically what it says is that, if there's rapid and large technological advances, bioenergy could be a considerably larger effective carbon sink than the reforest. That's this up here in this upper end of the uncertainty estimate. But with slower technological advances, biocrops could totally fail on its intended goals, and they could actually be a carbon source due to all that land use change and deforestation that happened. In terms of reforestation, the effectiveness, that there's a question of whether the environmental conditions support the growth of a healthy forest. So this is the map showing the change in trees and the reforest run, and this shows a gain in carbon. What you see is, there's gain in carbon in the tropics. That's CO2 fertilization. There's gain in carbon due to the reforestation effect. But in some places, you've planted forests, like here in the central U.S., and there's essentially no carbon gain. And basically, what we can find is that, if you look at that, there's some places around the world. If you focus here on these different probability density functions, some places in the world, this is the CO2 fertilization effect, where there was high and constant forest fraction. Those places tend to gain a lot of carbon in the future. And this is where there's basically grasslands. They don't gain carbon, that's as you expect. And then this gray curve here shows what happens for the reforested regions. And basically what it says is that in some regions, you're gaining quite a bit of carbon. In some regions, you're really not. We've actually been able to trace that back to the fact that in some places, the climate just does not support the growth of that forest. And here's a PDF showing different regions around the world, especially in the tropics where there's enough moisture, it does gain enough carbon. In places like the central US, where actually in CSM there's a low bias of precipitation, it doesn't gain any carbon. Also across Europe, it's really not gaining much carbon. So it really depends on where you find your forest, whether you're going to get something that looks like this or something that looks like this. Or in some cases, we even see that there's a loss of carbon. Okay, and then my last
Just
point.
FYI, you're at 10 minutes. Yeah.
Great. Okay, last point here is the disparate impacts in terms of the surface climate. So this is the difference in temperature for the biocrop versus reforest on the daily maximum 2-meter temperature. See, in the tropics, you're getting warmer conditions in the bioenergy expansion, as you might expect. So converting to croplands tends to warm the climate. But in the higher mid latitudes, you're actually seeing cooling in the bioenergy, and that's a little bit counterintuitive. You might have expected that if there's more forest, there would be cooling. What's interesting here is that in that biocrop scenario, you actually get enough cooling that it totally offsets all of the warming in some of these places around the world. And so why is that cooling happening? Well, it's mainly because of the fact that, like I said before, some regions, those forests don't grow. If the forests don't grow, you don't get the ET cooling, you don't get the the better mixing from the roughness effect, and you just don't get that cooling. So where newly planted forests go well, reforestation results in cooler temperatures. Where they don't go well, there'll be high bioenergy, food crop ET albedos drive cooler temperatures. So to summarize, the effective carbon sink associated with land-based mitigation is really dependent on a lot of assumptions related to Beck's technological advances, and also on what the environmental conditions are that support growth. There's a ton of caveats. The couple of climate biases really come into play here. And there's also a lot of land model structural limitations that are having a big impact. And furthermore, this is a single model study. We should do this with multiple models to see what the impacts are. We'll stop there.
Great. Thanks, Dave. And thanks to all of our speakers for a really interesting session. We've got about 10 minutes for open discussion. So if folks have questions for Dave or any concluding thoughts they want to share with the group, we would welcome all of those. Abby.
I didn't think I should call on myself. Dave, that's really interesting. I'm curious, you said it was due to changes in ET. Did you also check about the influence of albedo? Because I would guess the bioenergy crops would be brighter than the trees as well.
Yeah, there is albedo changes, and they are, except for in places where the forest doesn't grow. Mm-hmm. And actually then you can get a situation where it's not actually brighter with the bioenergy crops, so that whether or not the forest grow can have multiple impacts.
Mm-hmm.
Yeah.
Great. Open floor for questions. Gordon, go ahead.
Gordon.
Hi. Yeah, there was a real interesting discussion going on in the chat between Ichi and Guling Wang about the results from Song's and Ichi's presentation. And so I'd like to sort of follow up on that, because if the gist of it that I seem to get from the presentation and even then the chat was that, we might have to start, we're moving to this world where we're tuning up CLM and parameter estimation, but that's very much dependent on the model structure. We're moving into this world, I guess, where maybe we're going to have to retune the model every time there's a structural change to it. And so I'd like to hear Ichi's thoughts on that. Is that sort of really the implications of what was coming across from their study? Because We haven't really talked about that too much yet.
Gordon, it's a great question. And, recently I have thought about this issue a lot. And probably, most striking results was from CLM 4.0, when CLM 4.0 incorporated the nitrogen limitation, and then the global total soil carbon storage only gets to like 500 something, and in the real world, based on data, most of the time it's said about 2,000. So this issue kind of stuck in my mind, and then when Sean was interested in the issue, and we started to explore. And as you might know, my lab has been doing data assimilation for about 20 some years, and unfortunately, we do have to do reparameterization whenever we do model structure change. If we really want to do, to make the model to realistically simulate the ecosystem responses. So one of the line, in Song's presentation is that the real world process or even state will not change due to our model structure change. So that's basically a key line to me. And when we change model structure, like CLM 4.0, and then nitrogen limitation is so strong and make the total soil carbon storage become only 500 something. And so that's the point. That's real world process, and the state will not change because of our model structure change. Yeah, unfortunately. And also one thing is for modeling community, actually this is quite, we have used the model for 60 some years, but most of the time we tune the parameter to make the model simulation reasonable. But unfortunately, I understand most of you probably spend a lot of time and worked very hard to tune the model parameters, but none of the effort has been documented in the literature. And we understand that, we have discussed how to modify model structure, but the community hasn't paid enough attention on parameterization issue.
I want to just follow on that and say it seems like the implication from what you're saying is that you prefer a comparison more like ILAM, like benchmarking the models against the observations, whatever the structures are within that model, rather than the way that we often do a lot of experiments where we change one structural element and then look at how the answer is different, because that's not really a fair comparison if the structure should be tuned differently to the observations. Does that at all match up with what you're suggesting?
Well, I'm not sure if I fully, probably, can you say it again? Sorry.
Sure. I guess I mean, like, a really common way we might do something is add a new feature, or say, like we're talking about adding nitrogen cycling, and then we compare it to with or without that component, but that maybe isn't the right comparison. The right comparison is to compare the both separate structural versions tuned separately to some third independent thing, like ILAM might be used to like compare it against a benchmark.
Yeah, probably let me put, when someone submitted the manuscript, we get 2 reviews. The reviewer was stunned by the point we tried to make, and also they asked if you always tune your model, and what's good the model about. So the two review really forced us to think about this issue. You know, the why we need a model if you keep tuning, you know, whenever you change model structure, you tune again, you reparameterize it again. So if we take the nitrogen as an issue, you know, the conceptually, we want to use nitrogen model, carbon and nitrogen coupled model to examine how ecosystem respond to climate change under the nitrogen limitation issue. So we really, you know, the Song's work basically try to tune those during the period. And then basically when it applied to study the ecosystem responses to climate change, and then the key point is how to use that model to study nitrogen limitation influences instead of, you know, when we put the function of the nitrogen limitation into the model and lower the state variable or lower the rate variable. So this is not the point, I think, scientifically. I understand this issue. You know, this is quite serious issue for more, you know, if we really want to do modeling well to predict the real world responses. Yeah.
Yeah, it seems like, Abby, you would have to recalibrate every time to do this properly.
Yeah, I mean, it's obvious for really big things like adding nitrogen limitation when you didn't have it, but the implications are that it's always a problem.
Which is, of course, part of the motivation for trying to systematize this to make it so we can't actually repeat it. But well, it remains to be seen how feasible that is.
I was wondering if Nate might want to comment on, there was some stuff in the chat about an ocean parallel to ILAM. Do you want to just tell us briefly about that?
Sure. I mentioned I'm really bad at Zoom chat, so I'm not sure how much of it came through, but we've had what we call IOMB. Somebody suggested a different acronym, but for whatever reason, we settled on IOMB. The initial work was done by Olu Oluwaseun, and currently it's undergone by Weiwei Fu. So it does exist, and it's out there. Weiwei has a paper, hopefully to publish very soon on it. And we just don't tend to present as much on it, not being ocean people ourselves.
It seems relevant, though, that you would want to benchmark all the parts of the system. So
absolutely,
it's exciting to know that there's work there too.
There's some other challenges, I think, that we found with benchmarking oceans that we don't quite have in an analog to inland, but.
Great. Well, being mindful of the time, we should probably break, but thanks everybody for the excellent talks and the great discussion. I know that Abby, Matt, and I welcome continued thoughts about how we can move the BGC working group forward, especially now that Matt has joined as the new co-chair. So feel free to continue the discussion with us at any point if new ideas are prompted by the presentations today.
Yes, thanks everyone. Thanks for your talks and presentations and discussion.
Thank you.
Thanks.